Okay, so we're designing compression members. We're going to design a steel member under compression axial load. And what we're designing this member that it has some eccentricity in terms of its loading. So, for example, if we have an angle section here, that the loading, the elevation here, the loading be applied to one leg, but the centroidal section is somewhat a distance e, an eccentricity away from the load that's been applied. And we know that if we have an eccentricity and a load times the distance or times the lever arm will give us a moment. So therefore, as well as having an axial load along the length of this member, we also have a moment at the end of it. And that moment is induced because the load is applied as an eccentricity away from the centroidal section. That moment is the axial load, the compression axial load multiplied by the eccentricity. When I'm designing this section, I can design it explicitly for the axial load, a combined axial load and a moment. Or if I go to Eurocode 3, EN 1993, part 1, it tells me I can do two things. One is to either analyze the bending moments and include it in the design, or for light bolt sectional angle struts like what we have here, we can use an approximate method of Annex BB at the back of Eurocode 3, part 1. So that's what I'm going to do in this example. We effectively change the normalized sinus value to an effective normalized sinus value, and that will take into account the moment. In other words, we're going to increase the normalized sinus value a little bit to call it an effective normalized sinus value. That will take into account the eccentricity or the additional stresses applied due to the eccentricity. Okay, so method 2 is justified because the eccentricity is reduced away from the connection. So if we do a finite element analysis of that, we would see that we have higher stresses at the end for the moments, but that stress is quickly dissipates down the moment. It doesn't affect the stresses further into the member. And as such, methods have been accurately calibrated against test data. So for example, in Annex BB for rolled sector angles, for web struts, we have about the three different axes, the V, the Y, and the Z axis. Normalized sinus value 1.35 plus 0.7 times normalized sinus value about the V. 0.5 plus 0.7 times normalized sinus value about the Y. 0.5 plus 0.7 times normalized sinus value about the Z. Okay, but for us to be able to use this, we have to have at least two bolts in at the end of the section. We're connecting it. So if we have only one bolt, we can't use these equations. Okay, so this is the extract straight from Eurocode 3, part 1. Angles as web members. That's the three equations in there about the Y, V, Y, and the Z axis, where the normalized sinus value is defined in section 6.3.1.2 in the code. And as I said, yeah, you need to have at least two bolts. When only one bolt is used for the in connection of the angle members, the eccentricity should be taken into account using 6.29, the Booklet and LCR, taken as the section length. Okay, so we have to explicitly take into account if we have only one bolt in there. Okay. So we're going to look at this through the lens of an example. I find that's the best way to understand what's going on. So if we take an angled section here, like this one here, it's got an 80 length, so it's 80 high in one direction, 80 high in the other direction. It's got a thickness of 10 millimeters, so an 80 by 80 by 10 UKA, so it's an equal angle section. The steel is grade S275. It's part of a truss member, so in other words, it's just got compression load into it, axial compression load, and the length of the member is 2 meters long. Okay, and there's the axis that we're just referring to. So say the V axis, Y axis, Z axis, and U axis in there. And there's where the centroidal section is, distance C from the origin here, C in here and C up there. So it's C in both directions because it's obviously symmetrical, or it's symmetrical in terms of its length of its leg. So it's actually symmetrical about the UU axis there. Okay, so we're going to have to do 4 checks. Check for local buckling, flexural or known as lateral buckling, torsional buckling, and torsional-flexural buckling. So that's the 4 checks we're going to do. We'll step through the standard Eurocode 3 design procedure, where we first select the section and the grade. Then we're going to classify the section, whether it's a class 1, 2, 3, or 4 section in terms of susceptibility to local buckling. We determine the critical buckling length for each buckling axis. We'll then work out the normalized inverse value for each buckling axis and decide which buckling curve to use, and that will give us the imperfection factor. Use the imperfection factor and the normalized inverse value to work out what the reduction factor is, and then take that reduction factor and multiply it by the cross-sectional resistance, where for a class 1, 2, or 3 section, the cross-sectional resistance is the cross-section area times the normalized inverse value, times the nominal material strength divided by the material factor of safety, which in this case is just 1. Okay, so we then have to get this reduction factor for each of our different buckling modes, for the lateral buckling, for the torsional buckling, and the torsional-flexural buckling. Okay, so we have to work out this for each of the 3 ones. But effectively what we're doing is we're trying to find the normalized inverse value for each of the 3 different buckling modes. We work out then which is the most critical one in terms of our design. Okay, so for the torsional flexural buckling capacity in there, that will arise when the shear center, so shear center here is G in this example of a parallel flange channel, or in terms of an equal angle over here, there's the shear center G, and the centroid of the section O. So when the centroid of the section and the shear center don't match up, then we could get torsional flexural buckling in there. So the critical buckling capacity for torsional flexural buckling is the smallest root of the cubic equation in N. Okay, so it's the equation for the torsional flexural buckling, and this is the equation here. So we have y naught is the distance from the shear center to the centroid of the section along the y-axis. Z naught is the distance from the shear center to the centroid of the section in the z-axis. So in this case, we can see that the shear center and the centroid are both along the same axis, so therefore z naught is equal to naught, and y naught is equal to this distance here. Okay, so that's this first special case. We're a special case about the major axis. Sorry, we're symmetric about the major axis. In this case, it's symmetric about the major axis because we can see the top section here is a mirror image of the bottom section there. So that's symmetric. So therefore, z naught is equal to 0. And we know that I naught squared is equal to, so the radius gyration and subscript naught squared is the radius gyration about the major axis squared plus the radius gyration about the minor axis squared plus y naught squared plus z naught squared. So in this case, z naught is 0, so it's disappeared from that equation. So that's what the I naught value is there. N is the axial load. NCR is a critical buckling capacity about the y-axis. Critical buckling capacity about the z-axis is NCR-Z. NCR-T is the torsional critical buckling capacity in there. Okay, so that's the equation. So in this example here, where we have symmetrical about the major axis, like in an parallel flange channel, we can get z naught equals naught. That's I naught is equal to these guys here, radius gyration, and the equation is torsional flexural buckling equation, simplifies into I naught squared into N, which is the axial load, minus NCRY, critical buckling about the y-axis, N minus NCRT, torsional critical buckling, minus y naught squared, N squared equals naught. And then that gives you a quadratic equation coming out like this. Okay, so that's the quadratic equation coming out on the bottom, where you have the IY squareds, IZ squareds, and so on in there. Okay, so another special case. So in a T section, you have now got symmetrical about the minor axis case in here. Okay, because we can see that O and G are in the same line about the minor axis. So in other words, y 0 is equal, y naught is equal to 0 in there. Because if I put a mirror along the z-axis, I can see that the left is the mirror of the right. So therefore, y naught is equal to 0, and z naught is equal to this distance here. So therefore, my radius gyration, I know my y naught has gone out of the equation, so I'm left with radius gyration about the major axis squared plus radius gyration about the minor axis squared plus the z naught squared. And the equation for the torsional flexural buckling comes down to be I naught squared. So the radius gyration squared times N, the axial load, minus NCRZ, the critical talked about the minor axis, N minus NCRT, critical buckling or critical torsional buckling, minus Z naught squared, N squared equals naught. And then we simplify that equation down into a quadratic equation in there that we can solve. And the third special case is symmetrical about both the major and minor axis, like an I section, and then we would have Y naught is naught, Z naught is naught, and the equation comes out like this, and therefore torsional-flexural buckling is not an issue. Okay, so we're going to do this example, example 4, where we're going to calculate the buckling capacity of this section 80 by 80 by 10 UKA, which is grade S275, and it's in a truss. Its length 2 meters. And it's got a single angle connected into it. Okay, so the first thing I need to do is I need to go to the blue book in there. So this is the blue book. Okay, so this is the blue book. Oh, it's a blue book. Okay, or P363, steel building design is the official name for it, so it's the blue book. And then I'm going to page B39 in there. So when I go to page B39, that's going to give me the equal angle section. It gives me the dimensions and properties for it. We have the height of the leg in the other direction, the thickness of the section, the radius in here, the radius on the outside in there, and I can see the different axes, the x-axis, the z-axis, the v, and the u-axis in there. Okay, so then I go to the table, and then I get the section in it, and then I go all the way down and I get to the 80 by 80 by 10, which is the section that we're designing for. It tells me that it's 11.9 kilograms per meter, so every meter of this section I have is 11.9 kilograms. So I've got 2 meters of this section, so that's going to be 23.8 kilograms in total weight of steel, which will be maybe €2 or €2.50 kg, so that'll tell us how much we're going to cost us to buy it. We have the R1 and R2, the two radiuses, R1 and R2. With the area of the section, C m squared, so that's the cross-section area of the section in there. So obviously that's A, that's an important parameter that we need. Distance to the centroid C. So distance to the centroid C, so up here we have C, distance to the centroid from the origin, and C in centimeters. The second moment of area, it's the same about the Y and the Z axis in there because it's equal angle section. So that's 87.5. We have the area about the UU, VV, second moment area about the UU and VV axis across there. We've got the radius duration, so IY, IZ. So sorry, I'm putting these things in here. This is IY, IZ, IUU, VV. Then the radius duration, IY. IZ, IY, IU, okay, so they're all the radius duration. And then the elastic modulus, so we need the elastic modulus. Stop working. WY, WZ. We have the torsional constants IT. Okay, so the ones that we need to definitely take note of here that we will be using, so we're going to use the cross-section area A, which is 15.10 millimeter squared, so I'm just going to take a millimeter squared. Okay, I'm definitely going to use that. I'll probably use the second moment of area. So IYY equals IZZ equals 87.5 centimeters to the power of 4. Okay, so them two I'm going to use. Stick down the other ones. IUU is equal to 139 centimeters to the power of 4. IVV is equal to 36.4 centimeters to the power of 4. We're definitely using the radius duration, so IY equals IZ equals 24.1 millimeters That's 2.41 centimeters, so I'll just turn that into millimeters. IU is 30.3 millimeters. IV is equal to 15.5 millimeters. And this torsional constant, IT, there, that's there, is 5.45 centimeters to the power of 4. Yes, I'm going to need all those values. Obviously, the thickness of the section at some stage as well. It's 10 millimeters. And the height of the section, which is 80 millimeters. Okay, so we've got all those in there, and the actual warping constant, if we ever needed it, just because you've come across it before, is actually 0. So the warping constant for these guys are 0 in there. Okay, so that's the blue book. That's the sectional properties that we might need in there. So the first thing we're going to do is classify the section. So to classify the section, we need to work out what the yield strength of the section is. So we know that the thickness of the section is equal to 10 millimeters. And it's grade S275 steel. So that means so T is less than 40 millimeters. So that's T is less than or equal to 40 millimeters. That implies Fy is equal to, so it's 275 steel. Fy is 275 newtons per millimeter squared. And just if we needed so the ultimate strength is 430 newtons per millimeter squared. And that comes from table 3.1. Okay. All right, so what I'm doing is I'm just bringing up the tables with you, so you don't obviously have to take down all these tables. If you're taking down the notes and following me along, these tables are straight from the code. You should have the code open in front of you, but just so that you can see, I'm taking the snippets out of the code so we can see. So effectively, once we know that T is 10 millimeters, grade steel is S275. That means the thickness is less than 40 millimeters. And from table 3.1, we have the yield strength of the material is 275 newtons per millimeter squared. Okay, so then we can go to table 5.2 in the Eurocode 3, Eurocode 3, part 1. We've used the first sheet and second sheet looking at the webs and looking at the flanges, but if we actually look at the third sheet of table 5.2, and sheet 3 of 3 in Eurocode 3, part 1, we can see that there's also classification for angle sections and classification for tubular sections as well in there. So we've got an angle section in here. So we just have to check to see if it's a class 3, if it's less than this value here. So if the height of the section divided by the thickness of the section, so the height divided by the thickness, is less than or equal to 15 epsilon, where epsilon is the square root of 235 Fy. And in this case, we have 275 for Fy, epsilon is 0.92. Then if this holds true, that H over T is less than 15 epsilon, then it's class 3 section. Otherwise, it's a class 4 section. Sorry, if H over T is less than 15 epsilon and B plus H divided by 2T is less than 11.5 epsilon. If both of those hold true, it's it's at least a class 3 section. Otherwise, it's a class 4 section. Let's do the calculations for that. Okay, so we know that epsilon is equal to the square root of 235 over Fy, which is equal to the square root of 235 over 275, and we can see it's 0.92 from down the bottom here. So 0.92, we have 275 for Fy, epsilon is equal to 0.92. So that's table 3.2, sorry, 5.2. Okay, so H over T, so height is 80 millimeters, divided by thickness is 10, it's 8 millimeters, that's 8. And that's less than or equal to 15 times epsilon, which is 15 times 0.92. Okay. then B plus H all over 2T equals AT plus AT all over 2 times 10. Right, so that's equal to 8. And again, that's less than or equal to 11.5 epsilon, which is equal to 11.5 times 0.92. So that implies that it's a class 3 section. Came from table 5.2. Okay, so we've defined it as a class 3 section. Okay, so that's step 1 done, classification of the section. Again, the main thing is you note that that's table 5.2. This is the third sheet in that, which had the angle sections in it, and that gave us new limits for the section. So if it's a class 3 section, then when we go into the clause 6.2.4 compression, that tells us then that the design resistance for a class 3 section, class 1, class 2, or 3 section, comes from equation 6.2. Okay, so we're doing the cross-section resistance here. Step 2 is cross-sectional resistance, which we're going to do according to 6.2.4. 6.2.4. And we have in CRD as equal to the cross-section area times the yield strength all over the material factor of safety, which is from equation 610. Yeah, where so we add the cross-sectional area, which is 1510 millimeters squared. It came from the blue book. So remember, we just got that straight out of the blue book. 15.1 centimeters squared, which is 1510 millimeters squared. So that means that the cross-section resistance is equal to the area, so 1510 millimeters squared, times the yield strength, which is 275 newtons per millimeter squared, all divided by 1. Which is 415 10 to the power 3 newtons. And then if I divide that by the 1000, I can get 415 newtons. So that's a cross-sectional resistance of the section. Okay, so that's step 2 done. So step 1 was classification of the section. In other words, check how susceptible it was for local buckling. Step 2 is the cross-section resistance. And now we're on to step 3, which is going to be the flexural lateral buckling. So flexural lateral buckling, we're going to do according to clause 6.3, Eurocode 3, part 1. I've just taken out the extract here from the code so that we can follow along, instead of having to flick into the code and back out of it, so you can see where it is. So this is a uniform member in compression, which is what we have. All was we have to make sure that our demand is less than our capacity in there. And then for the design buckling resistance of a compression member, we have a class 3 section, so we're going to use equation 6.47, where the buckling resistance is this reduction factor times the cross-section resistance, which is just area times Fy, divided by the partial factor of safety. And the reduction factors depends on which the relevant buckling mode we're doing. So if we're using flexural buckling, then it'll be a reduction factor for flexural buckling. If it's torsional buckling, this is a reduction factor for torsional buckling. Or if it's torsional-flexural buckling, it's the reduction factor for that. Okay, so that's the equation that we're going to use. Okay, so that's the main equation we use, because it's a class 3 section. Okay. Okay, so then on to, that's clause 6.3.1 part 1 with buckling resistance, and then we go on to 6.3.1.2, next page into the code, and that tells us that this reduction factor, equation 6.49, we have these values phi and the normalized stiffness value, lambda bar squared. We know the normalized stiffness value, we can get it from the cross-section resistance divided by the critical buckling capacity, and again depends on which critical buckling force we're talking about, whether we're talking about lateral buckling, lateral torsional buckling or torsional buckling. That's the critical value that we put in there. We can also get that value from being the normalized value divided by the reference value. We need to put in into this phi value, as well as the normalized stimulus value. We need to put into the imperfection factor. That depends on which buckling curve we're going to use. If we're going to use buckling A, B, C, or D, that gets the imperfection factor. Once we have those two values, we can get the phi, and then we can put them in there and get the reduction factor. And of course, we can't have that value any greater than 1. The buckling capacity can't be any greater than cross-sectional resistance. Okay. So as I mentioned earlier on, then for the normalized stimulus value, to take into account for an L section or an equal angle section, that we have potential that we have some buckling some bending at the end of it because the loading is eccentric to the centroid of the section. We can go then to Annex BB in there. So at the back of Eurocode 3, Part 1, Part 1. Annex BB will tell us actually for flexural buckling of members in a triangulated and lattice structures. So like the truss that we're designing, then we can use this to work out an equivalent normalized stimulus value or an effective normalized stimulus value for the section. So if we're talking about chord members in there, outer plane buckling of web members, buckling length is taken as the length of the system. So in other words, telling us here that the buckling length is the overall length of the member, unless a smaller value can be justified by analysis. So in all cases, almost all cases, we take the length of our member, full length of the member as being the buckling length. So if I have a truss, I'm designing. Okay, so whatever length the member is, that's the length of the member there. The critical buckling length is equal to the overall length of the member. Okay, so that's what that first part of the clause is saying there. The buckling length for an I or a H section can be taken as 0.9 for in-plane buckling or 1 for out-of-plane buckling, unless a smaller, a different value can be taken. So we could actually, if we had an I or a H section, we can take it as a bit shorter for in-plane buckling, the critical buckling length. So we can take LCR equals 0.9 times L. The third part there, web members may be designed for in-plane buckling using the buckling length smaller than the system length, provided that the cord supply appropriate end restraints and the end connections supply appropriate fixity. Okay, so if we're going to put some fixity at the end for some of the members, the web members, so not the cord members, so that's the cord at the top, bottom cord, the cord members, top and bottom, the web members are in between. For those members, we could take a shorter length than LCR. Sorry, that's the cord here. Okay. So under these conditions, it's normally that LCR for in-plane buckling can take 0.9 L. So we could, if we wanted to, when we're designing some of these members, the web members in here, we could take the length LCR as being 0.9 times L. Okay, so this member here. So we could take LCR equals 0.9 L. Okay, so that's L there. Okay, so I've took that length there, that web member there, the web. Okay. So that's what that tells us. Okay, so then if we have angles as web members, so in here if we have an angle, so like what we have in our example that we're doing, we have an angle in there. So provided the cords supply appropriate end restraints to the members, the angles, and the end connections to the web supply appropriate fixity, in other words, so we have at least 2 bolts here at the end of the members, then the eccentricities may be neglected, and the end fixity is allowed for in the design of the angles as members in compression. The effective slenderness values can be used here. So I'll just bring that up a bit bigger. So the effective slenderness value here, about the v-axis, 0.35 times 0.7 times normal slenderness about the VV axis. Effective slenderness about the y-axis is given by that equation there, 0.5 plus 0.7 times normalized slenderness about the major axis, y. About the minor axis, normalized effective slenderness value, 0.5 plus 0.7 times the normalized slenderness about the ZZ axis. And the normalized slenderness is defined clause 6.3.12 in Eurocode 3, part 1. Okay, and then as I mentioned, when only 1 bolt is used for the end connection of an angle member, the eccentricity should be taken into account using 6.2.9, and the buckling length should be taken as equal to the system length. So in other words, we have to take into account that we have a combined bending and axial for that situation. And then for hollow members, if we have for hollow members, the buckling length of a hollow member may be taken as 0.9, both in plane and out plane directions. Okay, so for okay, so if we have a hollow section in there, sorry, the whole thing is frozen. So if we have a hollow section, okay. So for a hollow section, again, it's part of a truss system. Okay, so this is a cross section XX. So if I have a hollow member there, what it tells me is that I can take buckling capacity, so L critical equals 0.9 times the length. Okay, so that's the overall length. For a chord member, and for a member that's a web member, it can be taken as 1. So that's the chord member. If I take a web member like this guy here, it's L, and then LCR equals 1 times L of the web. Okay, so that's L of a web, L of a chord. Okay, so just have to be careful there with so sometimes we can use 0.9 internally. So if we have an angle section, we can use 0.9 times the length of the web for the critical length. For the chord, it's 1 times L. Whereas then when we look at the for hollow sections, it's telling us for the chord member, we could use 0.9 times L, and for the web member, if a hollow section using that, we'd have to use 1 times the length of the web. We could conservatively always use 1 times the overall length for the buckling length if we want to. Okay, so that's the buckling. So what we're going to do is obviously we need to start to work out what this normalized slenderness value, or sorry, the imperfection factor is first, and then the normalized slenderness value in there. So we look at the section we've got. So we've got an angle section which is down here. So it's an L section. No matter which curve we're buckling about, which axis we're buckling about, we're always going to use buckling curve B. So we're at S275 steel, we're going to use buckling curve B. So that's so we're here. This guy, buckling about any curve, buckling curve B, because we have S275 steel. Okay, so table 6.2 implies for UK equal angle section, use buckling curve B. Okay, and then if we're using buckling curve B, then we've got table 6.1 implies that the imperfection factor alpha is equal to 0.34. Okay, so we've got the imperfection factor is 0.34 in there from using table 6.1. Okay, so that's that. Now we also need to work out what the normalized slenderness value is. Okay, so we're going to say so we're going to look at flexural buckling. So we can do both YY and a ZZ together, because we looked from the table, we could see from the blue book it has the same properties about the about the YY and ZZ axis. So in the question we're given the length of the member, and we're going to take that as equal to critical length is equal to 2 meters. And we know that the slenderness value is equal to critical length all over I y. So the critical length here is 2 meters, 2000 millimeters. And the second moment of area, we got from the blue book. Back and see what I had. Second moment of area. Sorry, the radius of gyration is 24.1. That's y. Okay, so there it is, 24.1 millimeters. So that's 24.1. So 1 divided by the other there gives us 83. And then we know that the normalized slenderness value is equal to the normal slenderness value divided by the reference slenderness value is 83. Divided by the reference slenderness value, which is, what was it, 93.9 epsilon. Okay, so where we had that. Okay, so 93.9 epsilon. Epsilon is 0.92, which we worked out earlier on. So the normalized slenderness value 0.956. Okay, then from, we just looked there a second ago. Now from Annex BB, we said that the effective value, take into account of that eccentricity at the end, that will give us a moment at the end of the member, equal to 0.5 plus 0.7 times the normal slenderness value. And that's, you get that from equation, so Annex BB, equation BB1, that we just looked at there a second ago. So that's 0.5 plus 0.7, 0.956. Which is 1.17. Okay, so we can see there that it was 0.956, and then to take into account that eccentricity at the end, that was going to give us a moment. Instead of having to explicitly design for the combined moment and an axial load, we can change the normalized slenderness value and increase it from 0.956 up to 1.17 in there. And we know from the curve with normalized slenderness value against capacity, the bigger the normalized slenderness value is, the smaller the capacity of the section is going to be. Okay, so now we have the normalized slenderness value in there. We have the alpha value in there from up here, 0.34 of normalized slenderness value. So now we can get the phi value, and then we can get the reduction factor. Okay, so let's do that. Okay, so phi equals to 0.5 into 1, so plus alpha into the normalized slenderness value minus 0.2 plus normalized slenderness value squared. And we're looking about the y-axis here at the moment, so we put in little y's. What is that? So that's equation 6.49. So what do we work out? 0.5 into 1 plus 0.34. Normalized slenderness value 1.17. So it's the effective value that we're putting in there, plus 1.17 squared equals 1.35. And then the reduction factor the y-axis is equal to 1 all over 5 plus the square root of phi squared minus lambda bar squared. I think that's the same set of equations, 6.49. So that's 1 over 1.35 plus the square root of 1.35 squared minus 1.17 squared. And that gives me 0.495. Okay, so that's the normal resistance value. So then what's the buckling resistance? The lateral or the flexural. Flexural or lateral buckling about the YY axis. So NBY RD is this reduction factor and the cross-sectional area times the yield strength, all of the material factor safety in there. So the reduction factor, so it's only got about 50% of its capacity as a result of buckling. So if we can stop that buckling from happening, we could double its capacity. Then the cross-sectional resistance was the cross-sectional area is 1510 millimeters squared times 275 newtons per millimeter squared, 1 divided by 1. That's 206 × 10 to the power 3 newtons, which is equal to 206 kilonewtons. Okay, so that's about the YY axis. We said that also the NB Z RD is the same, because NBY RD equals 206 kilonewtons. Okay, so we said it because the slenderness is the same in both directions. So we want to do the same equation for about the ZZ axis, or sorry, so we need to also check about the V axis. Check about the V axis. Okay. Let's say. Okay, so I was going to check about the V-axis. So we have the CR about the V-axis again is equal to 2 meters. So we have no change in it. And the normal or the slenderness value about the V-axis is going to be the critical length about the V-axis, all divided by the radius duration about the V-axis. Screen gone. Okay, sorry. Okay, sorry, screen disappeared there for a second. Okay, so we're gone about the V-axis. So critical length is 2 meters. The slenderness value about the V-axis is equal to critical buckling length about the V-axis all over the radius duration about the V-axis. So we're 2,000 millimeters again, 2 meters, and then from the blue book, we worked out that the radius duration is 15.5 millimeters. So when we work those out, we get 129 as being the slenderness value. Then the lower slenderness value is the slenderness value divided by the reference value, which is 129 divided by 3.9 epsilon, which is 0.92. So I get 1.48 for that. And then again, we go to the Annex BB, and to get the effective value, to take into account those moments at the end of it, 0.35 plus 0.7 times the normal ascendance value. That's Annex BB. Equation BB.1. So that's 0.35 plus 0.7. That's 1.48. Yes, that's 1.39. Okay, so that's the normal ascendance value. So now we can work out what the phi value is. So again, it's 0.5 into 1 plus the alpha value, or the alpha value, which is the reduction factor, or the imperfection factor, 0.34, into the normal ascendance value, 1.39 minus 0.2. So it's we're just following the same equations I had last time. Plus 1.39 squared. That should come out to be 1.67. And then the reduction factor about the v-axis is equal to 1 over the phi value, which is 1.67, plus square root of phi 1.67 squared minus normal ascendance value 1.39 squared. Okay, so I'm just following all the same equations. Sorry, that was equation 649 we've used there. And again, equation 649. Just taking the exact same equations, just reapplying. So that's 0.386, even lower than last time. So 0.495 about the YY and ZZ axis. This time it's 0.386. So the Booklet resistance about the V axis is going to be equal to this reduction factor times the cross-sectional resistance, all divided by gamma m naught. So 0.386 times the cross-sectional resistance, which is 1510 times 275 all over 1, which is 160 by 10 to the power 3 newtons, which is 160 newtons. Okay, so that's going to be the most critical out of all of those so far, obviously because it's smaller than the other two. So for flexural lateral buckling, it's about the VV axis, which is 160 kilonewtons is the capacity. Okay, so now we need to check for torsional buckling and torsional flexural buckling. Okay, so torsional buckling, so this is so we're going to use SN001 for this. Okay, so SN001 that we're using for torsional buckling in there. Okay, so just go back a sec. So the buckling resistance about the minor axis or about the V axis, I said is less, so that's 160 compared to 206 about the YY and the ZZ axis. So we have so we've checked the cross-sectional resistance. We found that the cross-sectional resistance back here is 415 kilonewtons. So that's how much, if there's no buckling whatsoever, the section could take 415 kilonewtons. To lateral flexural buckling, we've checked the member, and when we go through the calculations, lateral flexural buckling about the YY Z axis, we get 206 kilonewtons, and we check about the V axis, 160 kilonewtons. Okay, so you can see how much smaller it is. Effectively, it's 39% smaller, or 39% of the cross-sectional resistance at 160 kilonewtons. Okay, so now we need to check for torsional buckling and torsional flexural buckling. So torsional buckling, back again. The first one calculated, please. Which is the first one calculated? you want me to go? This one, further back. Not far enough back. Just one at a time. What's his next zone? So this page here, we've got at the bottom of this page here, we've got the normalized slenderness value about the y-axis, 1.17. We took that forward with the normalized slenderness value in here. Okay, we took that normalized slenderness value of 1.17, plugged it in here, plugged it in there. The imperfection factor 0.34, which we got here. And then from that, then we had the phi value. Plug that 1.35 into the equation 6.49 for the reduction factor 1.35. Also put in the normalized slenderness value in here 1.17. We got 0.495, and from that then we got the flexural buckling about the y-axis by plugging in basically 50% of the cross-section resistance. So that gives us 206. And then we did the same thing then about the v-axis, got 160. Now we're going to look at the torsional buckling resistance in there. So we, because Eurocode 3 part 1 doesn't tell us how to work out the critical axial load for torsional buckling, I'm going to use SN001 for that, where we have a greatest duration value in there, G, which is the shear modulus, I, which is the second moment, or the torsional constant, IW is the warping constant, and so on in there. So what do we say? So that's the equation that we're going to use. Okay, this equation here that we're going to use. So what's handy is this all becomes 0 by that bit, because IW is equal to 0. Okay, so we then have N, C, or T is equal to I over I naught squared into G I T. Because we have no warping constant because it's 0 for this section. Okay, so that's from that equation there. Okay, so sorry, that's critical. Let's see. And now we have so we have I naught squared is equal to I y squared plus I z squared plus I y naught squared plus z naught squared. So that's all the ones that we need in the equation. We draw up the little section up here. We have. Okay, that's the section. Remember that that's. Oh, come on. Yeah, that's one height. Another height here. Thickness there. We have an axis through here, which is a basically symmetrical axis, which is U. Then from that we have that V, which is parallel to that, perpendicular to that, sorry. And we would have, let's see here, Z that way and Y that way. It's Y, that's Z. Okay, so they're all our axes that we have there. So what are we interested in? Well, we'll have to try and work out these Y naught and Z naught and so on. If I go to the center of the section through there and put say the origin there, O, it's the origin. Distance from the outside edge to the origin, that's obviously the thickness divided by 2. Okay, distance from the origin. Then where all of these guys cross over each other, which is the shear center here, G, the shear center. So that's going to be C1 from over, and then overall the C value. C is from the outside edge into the shear center, which we can get straight from the blue book. Okay, so O is a centroid, and G is the shear center. So from up there, I've got C1 is equal to C minus T over 2. C I get from the blue book. So that's 23.4 minus 10 mil over 2. So final way from that is 18.4 millimeters. Okay, so that's the C1 value, 18.4 millimeters. Okay. So as we go, come on, as we are considering a torsional buckling. So we saw that about the V-axis was critical for the lateral buckling compared to the Y and the Z-axis. Oh, the pen is out of juice. So we're looking about the V-axis. Then we have the rate of duration that we're looking at. It's going to be, instead of Y's and Z's, we're turning those into U's and V's. Okay. So we got IU straight from the blue book, which is 30.3 millimeters squared. The V value was 15.5 millimeters squared plus U naught. U naught value there, so that's U naught. U naught value. So U naught is going to be equal to U naught squared is equal to 2C1 squared, which is effectively from it's going to come from Pythagoras' theorem. I'm not draw too much up on top of this one, but if I draw a green box up here, so C1 is this distance across here. C1. I want to know what U naught is, which is this distance along here, the diagonal on the U axis. If I draw in that as a little triangle, we can see that's Pythagoras' theorem. So I draw it out here. Okay. So I have a C1 here. Now on it, I want to know what U naught is there. So I know that, and if I call this value here, this is a Z and naught. Height from there. So from that I know that, and I know that C1 and so C1, sorry, that's Y naught. C1 and Z1 is equal to C1 as well. So I know from Pythagoras' theorem that U naught squared equals to C1 squared plus C1 squared. Okay. And then that's obviously U naught squared equals 2C1 squared. So that's just Pythagoras' theorem. Pythagoras theorem. Okay, so that's how we got that U naught value out of. So I'll put in U naught here, 2 times C1. So U naught squared is 2 times C1. So C1 being 18.4 millimeters squared. And V naught is just equal to 0. Okay, because we can see there. So this is U naught in this direction, this is V naught in this direction, so we can see that it's along the same line. See, we're not up and down V, so it's along the same line, so it's equal to 0. Okay, so U naught squared is the same as, or sorry, V naught squared is equal to 0. Okay, so from that then, when I work on that, I naught squared is equal to all that, so there I naught is equal to 42.8 millimeters. Okay, so now I've got the I naught that I need for the equation here. So if I naught squared G I know is 80,770, and IT I got straight from the blue book. Okay, so in CRT, so the critical buckling for torsion equal to 1 over I naught squared into GI torsional constant is 1 over 42.8 millimeters squared. G is, what was it? 80,770. So 80,770 newtons per millimeter squared. And I of T is 5.45 by 10 to the power of 4 millimeters to the power of 4. Put all that into the equation there. I get 2405 by 10 to the power of 3 newtons. Just 2405 kilonewtons. Okay, so kilonewtons. Okay, so because remember, I warping is equal to 0, so that's why we haven't got the second half of that equation there that we would normally have. And then normally send this value. For a torsional buckling. Is equal to the cross-sectional resistance divided by the critical resistance. And we had the cross-sectional resistance was 415 kilonewtons from earlier on, 2405 from here. And that gives us 0.416. And you'll see that from equation 652. Is that? Okay. And then if you go to clause 6.3.1.4 part 3, it's going to tell us to use buckling curve for table 6.2, appropriate for the ZZ axis. Okay, so it says that when we're looking at torsional buckling, we basically use the buckling curve about the ZZ axis. So in other words, so i.e. Here is buckling curve B. In this case, actually, because it's an angle section, doesn't matter whether it's which axis it is, because it's the same for both axes. And I'm not going to go through all the equations again, but effectively, when you do that, so that buckling curve B, so that's alpha is 0.34, the reduction factor. You should put that into the equations again, and you're going to get y is 0.623, equation 649, and you'll get the reduction factor. This is for torsion. The reduction factor 0.920. equation 649. And then you get the buckling, torsional buckling resistance, which is the reduction factor, obviously, times the cross-sectional resistance. And we have naught. Put that in there and you get 382 kilonewtons. Okay, so that's the torsional one done. 382 kilonewtons. Done all that. So that's torsional buckling done. So it's lateral buckling, torsional buckling, and now we have torsional-flexural buckling to do the last part. So I'll finish off recording the last part separately. I'll just do it in an hour later on today, so you have it, where I'll explain the torsional-flexural buckling part of it. So we're following, for torsional-flexural buckling, we're effectively following the same SN001 with some equations in there from it. So I'll record that later on in the today, so I'll have basically that full example done today, and then on Friday I will do the T section on the Friday's class. So therefore you have everything you need for the compression design member. You should have everything you need for your submission on Wednesday, for this Wednesday, and you will, and we've already gone through everything you need for the tension member in there.